There could be 10,000 civilizations in the Milky Way right now. That is not science fiction. That is the output of reasonable estimates using confirmed astrophysical data. 10,000 species building cities, launching satellites, asking whether anyone else exists. And not a single one of them will ever know about any of the others. Not because the universe is empty, because the universe is built wrong. The distances are too vast, the signals are too slow, and the windows are too short. Every civilization rises, looks out into the darkness, waits for an answer that will never arrive, and eventually goes silent. Then another one appears somewhere else and does exactly the same thing. The cosmos may be teeming with minds that live and die believing they are completely alone. This is why. If this is the kind of question that keeps you staring at the ceiling at 3 a.m, I would really appreciate it if you hit that like button and subscribe to the channel. It helps more than you might think, and it means we get to keep making these deep dives together. Now, settle in, get yourself comfortable, let's begin. You already believe they are out there. You might not say it out loud. You might not have thought carefully about the evidence, but somewhere deep in your reasoning, you carry an assumption so natural it feels like common sense. If civilizations can arise in the universe, then eventually, given enough time, some of them should find each other. This belief is not irrational. It is built on a lifetime of pattern recognition, on historical precedent, on a species-wide experience that says isolation never lasts forever, and it is almost certainly wrong. To understand why, we need to trace where this assumption comes from, because the instinct that existence leads to encounter did not emerge from astrophysics. It emerged from growing up on Earth, and Earth is the worst possible teacher for understanding how contact works across the cosmos. Think about the history of human exploration. Every isolated culture on this planet was eventually found. The Polynesians crossed thousands of miles of open Pacific in wooden canoes and reached islands that no human had ever seen. The Norse sailed to Iceland, then Greenland, then the coast of North America 500 years before Columbus. European explorers contacted indigenous peoples across Africa, the Americas, Southeast Asia, and the remote Pacific within a few centuries of sustained maritime expansion. Even the most geographically separated human populations, communities in the highlands of Papua New Guinea that had lived without outside contact for tens of thousands of years, were eventually reached during the 20th century. No group stayed hidden forever. No island remained undiscovered. Given enough time and enough motivation, every pocket of humanity was drawn into contact with the rest. This pattern trained our intuition. We internalized a principle that felt universal. If people exist somewhere, other people will eventually reach them. Distance creates difficulty. Oceans create delay. Mountains and deserts create barriers. But none of these obstacles prove permanent. Exploration always won eventually. Contact was always a matter of when, not whether. But we never stopped to ask why exploration always won on Earth. We treated it as a self-evident truth, an inevitable consequence of enough people existing across enough time. It is not. Exploration succeeded on Earth because of a specific set of structural features that happen to characterize this particular planet. Every one of those features is absent at galactic scales, and recognizing exactly which features made earthly contact inevitable is the key to understanding why cosmic contact may be structurally impossible. The first feature is simultaneity. Every human culture that has ever existed on Earth coexisted with every other human culture of its era. No expedition ever reached an island only to discover that the civilization there would not arise for another 10,000 years. Contact on Earth was guaranteed in part because all human populations descend from the same recent ancestor. We are a single species that radiated outward from a common origin roughly 300,000 years ago. By the time any group developed the technology to search for others, the others were already there, already present, already contemporaneous. The temporal overlap was not a lucky coincidence. It was a structural certainty built into the biology of a single species dispersing across a single world. In the galaxy, this simultaneity does not exist. Civilizations do not share a common ancestor. They do not arise from the same originating event. They emerge independently, on different worlds, around different stars, at different points in a timeline stretching across 13 billion years. There is no guarantee, and in fact very little probability, that any two civilizations will be active during the same era. The temporal overlap that Earth provided for free is something the galaxy does not provide at all. The second feature is proportional distance. On Earth, the distances between human populations were large relative to walking speed, but small relative to the available transportation technologies. Even the most remote terrestrial locations, the interior of Antarctica, the deep Amazon, the highlands of central New Guinea, were reachable within a single human lifetime using the technology of the era. The critical point is not that the distances were small in absolute terms. Some of them were enormous by any human standard. The critical point is that the distances were small relative to the speed at which explorers could travel, and relative to the lifespan of the cultures doing the exploring. A civilization that could build ships lasting decades could reach any point on Earth within a generation. The ratio of distance to speed to lifespan was always favorable. The planet's geography challenged human ingenuity, but never exceeded it. In the galaxy, this ratio inverts catastrophically. The distances between stars are not merely large. They are large relative to the fastest speed anything can travel, which is the speed of light. And they are large relative to the lifespans of the civilizations attempting to cross them. Even at light speed, the absolute maximum permitted by physics, crossing the galaxy takes 100,000 years. At any achievable fraction of light speed, travel times between neighboring stars stretch into centuries or millennia. The ratio of distance to speed to lifespan that made Earth exploration inevitable makes galactic exploration functionally impossible. The third feature is a connected medium. Earth has one continuous ocean. The Atlantic connects to the Pacific, connects to the Indian, connects to the Arctic. A ship launched from any coast can, in principle, reach any other coast without leaving the water. The ocean is a single unbroken highway linking every continental shoreline. Similarly, Earth has a continuous atmosphere. Sound travels through it, birds fly through it, weather systems cross it. The planet does not contain impassable voids between its habitable regions. Every landmass is connected to every other landmass by traversable ocean, or, during ice ages, by land bridges. Earth's geography contains barriers, but no absolutes. No region of the planet is separated from any other by a medium that is physically impossible to cross. Space is the opposite. Between stars lies vacuum, effectively perfect emptiness extending for light years in every direction. There is no medium connecting one stellar system to another, no current to ride, no surface to traverse, no shared atmosphere to carry signals. Each star system is an island surrounded by a void so absolute that it makes the Pacific Ocean look like a puddle. Crossing this void requires carrying everything with you: fuel, food, air, water, shielding, and doing so for durations that exceed the operational lifetime of any machine or social structure ever built. The fourth feature, eighth, and perhaps the most subtly important, is that Earth exploration operated faster than cultural change. When a European expedition spent 3 months crossing the Atlantic, the civilization that launched the expedition still existed in recognizable form when the ships returned. The language was the same, the government was the same, the institutions that funded and organized the voyage were still functioning. The explorers could report their findings to an audience that remembered sending them. Contact on Earth worked because the travel time was short enough that both the sending culture and the receiving culture remained stable throughout the exchange. In the galaxy, travel and communication times exceed the rate at which civilizations change by many orders of magnitude. A signal sent to a star 1,000 light-years away takes 1,000 years to arrive. During that time, the sending civilization may undergo revolutions, collapses, renaissances, and transformations so fundamental that the culture receiving any reply would bear no resemblance to the culture that composed the original message. The exchange does not connect two stable endpoints. It connects 2 points in a constantly shifting landscape of cultural evolution, and by the time the connection is made, both endpoints have moved beyond recognition. These 4 features, simultaneity, proportional distance, a connected medium, and communication faster than cultural change, are the hidden infrastructure that made contact inevitable on Earth. Remove any one of them, and earthly exploration becomes dramatically harder. Remove all 4, and contact becomes something that cannot be assumed, cannot be expected, and may not be possible at all. The galaxy removes all 4 simultaneously. This is why the analogy between human exploration and interstellar contact breaks down so completely. It is not that the galaxy is a bigger ocean, it is that the galaxy lacks every structural feature that made ocean crossing successful. Projecting Earth's history of contact onto the cosmos is not optimism, it is a category error. It is like predicting that fish will thrive in a desert because they thrived in the sea. The relevant conditions are entirely absent. Now project that flawed intuition onto the night sky. Look up and see 400 billion stars in the Milky Way alone. Consider that astronomers have confirmed planets orbiting the majority of those stars. Calculate how many rocky worlds sit in the habitable zones of their parent stars, where temperatures permit liquid water. Arrive at numbers like 20 billion, 40 billion, potentially hundreds of billions of worlds where the basic conditions for life might exist. Feel the weight of those numbers press against your inherited assumption. Surely, in a galaxy this rich, intelligence must have arisen more than once. And if it has arisen more than once, then the same logic that governed human history should apply. Civilizations should find each other. It is only a matter of time. This reasoning feels airtight. It is also catastrophically flawed. But seeing why requires that we first understand just how generous the universe appears to be with the raw ingredients for life. Start with stars. The Milky Way produces roughly 3 to 7 new stars every year. That rate has been roughly sustained for over 13 billion years, although it peaked much earlier in galactic history when gas was more abundant. The cumulative result is a galaxy containing somewhere between 200 billion and 400 billion stars at any given time. Some of those stars burn out and die, but new ones replace them in an ongoing cycle of stellar birth and death. The total number fluctuates, but the scale remains staggering. Hundreds of billions of nuclear furnaces burning simultaneously, scattered across a disk of space roughly 100,000 light-years in diameter. For most of human history, whether any of those stars harbored planets was entirely unknown. The assumption was widespread among astronomers, but direct evidence remained elusive until 1995, when Michel Mayor and Didier Queloz confirmed the first exoplanet orbiting a Sun-like star, 51 Pegasi b. That single detection opened a floodgate. Within a decade, hundreds of exoplanets had been discovered. By 2025, the confirmed count exceeded 5,700, with thousands more candidates awaiting verification. But the real transformation came from the Kepler Space Telescope, which operated from 2009 to 2018. Kepler stared at a single patch of sky and monitored the brightness of over 150,000 stars simultaneously, watching for the tiny dimming caused when a planet crosses in front of its host star. The results were revolutionary. Kepler demonstrated that planets are not rare curiosities. They are everywhere. Statistical analysis of Kepler data showed that virtually every star in the galaxy hosts at least one planet. Many host multiple worlds in complex orbital systems. Rocky planets roughly the size of Earth turned out to be the most common type in the galaxy, far more abundant than the gas giants that dominated early exoplanet surveys, simply because gas giants were easier to detect with older methods. The numbers that emerged from Kepler's data reshaped the conversation about life in the galaxy. Approximately 20% of Sun-like stars host a rocky planet in their habitable zone, the orbital region where surface temperatures could allow liquid water to exist. Apply that fraction to the estimated number of Sun-like stars in the Milky Way, roughly 20 billion, and you arrive at approximately 4 billion potentially habitable, Earth-sized worlds orbiting Sun-like stars alone. But Sun-like stars are not the only hosts worth considering. Red dwarf stars, which are smaller, cooler, and far more numerous, make up roughly 70% of all stars in the galaxy. Many red dwarfs also host rocky planets in their habitable zones. When you include red dwarf systems, the number of potentially habitable worlds in the Milky Way climbs toward tens of billions. Some estimates reach as high as 40 billion or more. The James Webb Space Telescope, which began science operations in 2022, has pushed these investigations further. Webb can analyze the atmospheres of exoplanets by studying how starlight filters through their gaseous envelopes during transits. Early observations have already detected carbon dioxide, water vapor, and sulfur dioxide in the atmospheres of several exoplanets. Webb observed the TRAPPIST-1 system, where 7 rocky planets orbit an ultra-cool red dwarf approximately 40 light-years from Earth, with 3 of those worlds sitting in the habitable zone. Preliminary atmospheric data from these worlds has been mixed. Some show thin or absent atmospheres, consistent with intense stellar radiation stripping away lighter gases. Others remain under investigation. Webb has also examined the sub-Neptune K218b, where tentative detections of dimethyl sulfide, a molecule associated with biological activity on Earth, generated enormous excitement, though the finding remains unconfirmed and debated among atmospheric scientists. The point is not that we have found life. We have not. The point is that the chemical building blocks, the right temperatures, and the necessary conditions appear to be startlingly common. This is where most people stop and draw the conclusion that feels obvious. Billions of habitable worlds, 13 billion years of galactic history. Surely intelligence must have emerged somewhere else. And if intelligence has emerged somewhere else, then contact should follow, the way it always has throughout human history. But that conclusion smuggles in an assumption so deeply embedded that most people never notice it. The assumption is that existence and contact are connected, that if minds arise in the galaxy, they will eventually interact, that the universe, given enough time and enough civilizations, will produce encounters between them. This assumption feels as natural as gravity, and it is the assumption that the rest of this story will take apart, piece by piece. Before we begin that demolition, we need to understand one more thing about how generous the numbers really look. Because the universe does not just provide habitable planets, it provides time. The Milky Way is approximately 13.6 billion years old. The Sun and Earth formed roughly 4.6 billion years ago. That means our star system arrived relatively late in galactic history, billions of years before Earth existed. Other stars were forming, other rocky planets were cooling, other oceans were potentially filling with liquid water. If life requires roughly the same developmental timeline it took on Earth, then civilizations could have arisen billions of years before humans evolved. The galaxy has had ample time to produce not just one, but thousands or even millions of intelligent species across its history. In 1961, astronomer Frank Drake proposed a simple equation to organize thinking about this question. The Drake equation multiplies a series of factors together to estimate the number of active communicative civilizations in the galaxy at any given time. The factors begin with the rate of star formation, then narrow progressively through the fraction of stars with planets, the number of habitable planets per system, the fraction of those planets where life actually develops, the fraction where intelligence evolves, the fraction that develop detectable technology, and finally, the average length of time such civilizations remain detectable. When Drake first presented his equation, most of the factors were pure guesswork. Today, thanks to Kepler, Webb, and decades of astronomical surveys, the first 3 factors are reasonably well constrained. Star formation rate, approximately 3 to 7 per year. Fraction of stars with planets, effectively 1 or very close to it. Number of potentially habitable planets per star with planets. Estimates range from 0.2 to 0.5 depending on stellar type and assumptions about habitability. These astrophysical terms are no longer mysterious. They are measured quantities. The remaining factors remain deeply uncertain. What fraction of habitable planets actually develop life? Nobody knows. We have exactly one example, Earth, where life appeared within the first several 100 million years after conditions became suitable. Some astrobiologists argue this rapid emergence suggests life is chemically inevitable wherever conditions permit. Others point out that a single data point tells us almost nothing about probability. Life on Earth could be a 1 in a trillion fluke that happened to occur quickly when it occurred at all. What fraction of life-bearing worlds produce intelligence? Again, unknown. On Earth, complex multicellular life took roughly 3 billion years to emerge after the first simple cells. Intelligence, as we define it, tool use, language, technology, appeared only in the last few 100,000 years, within a single lineage out of tens of millions of species. Some researchers argue that intelligence is a natural product of evolutionary complexity, virtually guaranteed given enough time. Others counter that nothing about evolution makes intelligence inevitable. Dinosaurs dominated Earth for over 160 million years without developing technology. Intelligence might be an extraordinarily rare evolutionary accident that happened to occur in primates on one planet. What fraction of intelligent species develop technology capable of interstellar communication? This question is even harder to answer. On Earth, the gap between cognitive intelligence and radio-transmitting civilization was roughly 200,000 years. Anatomically modern humans existed for most of that period without anything resembling electronic technology. The transition from agricultural society to radio astronomy took approximately 10,000 years. Whether this trajectory is typical, unusually fast, or unusually slow is completely unknown. And then there is the final factor, the one that matters most and is understood least: L. The average length of time a technological civilization remains active and detectable. This variable dominates the Drake equation's output. If civilizations typically last 10 billion years, the galaxy should be teeming with them right now. Millions of active cultures broadcasting signals and building megastructures. If civilizations typically last 10,000 years, only a handful might exist at any given moment. If they last only a few hundred years, we might be the only one currently active in the entire Milky Way. Historian Michael Shermer analyzed 60 historical human civilizations and calculated an average lifespan of 420 years. Using only civilizations more recent than the Roman Empire, the average dropped to 304 years. These are sobering numbers, though they describe political and cultural continuity rather than technological survival. A more recent analysis, published in 2024, used Bayesian statistical methods combined with the observed absence of any detected technosignatures to constrain the likely value of L. The conclusion was striking. Under the most optimistic assumptions about the other Drake equation factors, L is likely less than 5,000 years. Under moderate assumptions, it could be far shorter. But here is what matters for our purposes. Even if you feed the Drake equation optimistic values, even if you assume life is common and intelligence is a natural evolutionary outcome, the equation produces results that sound encouraging at first glance, but become deeply unsettling when you think carefully about what they mean. Drake himself suggested that approximately 10,000 civilizations might exist in the Milky Way at any given time. Other estimates using moderate assumptions have produced figures ranging from a few dozen to several 100,000. A 2020 study by researchers at the University of Nottingham estimated approximately 36 active communicative civilizations in the galaxy. Assuming Earth-like developmental timelines, these numbers sound hopeful. 36 civilizations means we are not alone. 10,000 civilizations means the galaxy is practically crowded. Hundreds of thousands would make it a bustling metropolis of intelligence. But none of these numbers tell you what you actually want to know. They tell you how many civilizations might exist. They say absolutely nothing about whether any of them can reach each other. Imagine a galaxy containing 10,000 active civilizations right now. Spread them evenly across the Milky Way's disk, and the average distance between neighboring civilizations is approximately 1,700 light-years. That means a signal traveling at the speed of light, the fastest anything can move in this universe, would take 1,700 years to travel from one civilization to its nearest neighbor, A round-trip exchange, a message and its reply, would take 3,400 years. 3,400 years ago, the Bronze Age was ending in the eastern Mediterranean. The city of Troy had recently fallen. Moses, if he was a historical figure, had not yet been born. The idea that a civilization could maintain a coherent technological identity, remain interested in the same questions, and still be listening for a reply after 3,400 years is not just optimistic. It is an assumption with no supporting evidence from any civilization that has ever existed on Earth. And that is the optimistic scenario with 10,000 civilizations. If the true number is 36, the average distance between neighbors stretches to approximately 17,000 light-years. A round-trip message takes 34,000 years. Human civilization in its entirety, from the first agricultural settlements to this moment, spans roughly 12,000 years. The reply to any message we sent would arrive long after every institution, language, nation, and possibly every biological descendant of current humanity had vanished. This is where the intuition breaks. On Earth, exploration worked because the distances were finite and the explorers were persistent. The Pacific Ocean is vast, but a canoe can cross it in weeks. The Atlantic is wide, but a sailing ship can traverse it in months. Even the most remote terrestrial destinations were reachable within a single human lifetime using the technology available at the time. The key feature of earthly exploration is that the distances, while challenging, were proportional to the capabilities and lifespans of the explorers. In the galaxy, this proportionality collapses entirely. The distances are not merely large, they are large relative to the speed of light, which is the absolute maximum speed at which information, signals, or influence of any kind can propagate through space. And they are large relative to the lifespans of the civilizations that might attempt to cross them. These two facts together create a situation that has no analogue in human history. No earthly culture ever faced a barrier where the fundamental speed limit of the universe made even communication with the nearest neighbor take longer than the communicating society was likely to survive. This is the trap built into the Drake equation. The equation asks how many civilizations exist. It does not ask whether any of them can interact. It counts inhabitants without asking whether the city they live in has any roads connecting their houses. It tells you the galaxy might be populated while saying nothing about whether that population can ever become a community. And here is what makes this genuinely disturbing. The numbers that make the galaxy look populated are the same numbers that make contact look impossible. A galaxy with 10,000 civilizations sounds encouraging until you realize that 10,000 civilizations spread across 100,000 light-years of galactic disk means each one is surrounded by a vast desert of empty space. And deep time. Increasing the number of civilizations helps, but not enough. Even 1 million civilizations would place neighbors an average of approximately 370 light-years apart, still demanding round-trip communication times of 740 years, longer than any continuous cultural or political institution in human history has maintained a consistent technological program. The instinct you carry, the one that says many civilizations must eventually lead to contact, was forged on a planet where every culture coexisted with every other, where the longest ocean crossing took weeks, where a shared ocean connected every coast, and where explorers returned home to societies that still remembered sending them. That instinct has never encountered a universe where civilizations arise millions of years apart, where the nearest neighbor might be millennia away at the speed of light, where no medium connects one island to the next, and where the very act of reaching out takes longer than civilizations tend to last. Everything you are about to learn builds on this foundation. The galaxy may be rich with worlds. The conditions for life may be common. Intelligence may arise again and again across cosmic history. But none of that guarantees what your intuition promises. The universe is not structured like Earth. The rules that governed human exploration do not apply at interstellar scales. And the reason the night sky is silent may have nothing to do with whether anyone else is out there. It may have everything to do with the architecture of space and time itself. What comes next will show you the first wall that makes contact between civilizations not just difficult, but physically, structurally, perhaps permanently impossible. And it begins with a number that sounds simple but contains within it the most absolute boundary in all of physics. The speed of light, 186,000 miles per second, the universe's maximum speed, and the galaxy's most effective prison. Nothing in the universe moves faster than light. This is not a limitation of current technology. It is not a barrier that cleverer engineering might someday overcome. It is a structural feature of reality itself, woven into the geometry of space-time by the equations of special relativity. Albert Einstein demonstrated in 1905 that as any object with mass accelerates toward the speed of light, the energy required to push it faster increases without limit. At the speed of light, the energy required becomes infinite. No engine, no fuel source, no technology conceivable within known physics can accelerate a physical object to that speed. Light moves at approximately 186,000 miles per second. That is the ceiling, and the ceiling does not care how advanced you become. On Earth, this speed limit is invisible. Light crosses a room in a billionth of a second. It bounces from the moon and back in about 2.5 seconds. Even at planetary scales, the delay is manageable. Signals reach Mars in somewhere between 3 and 22 minutes depending on orbital positions. Controllers at NASA's Jet Propulsion Laboratory have learned to work with these delays, programming rovers to operate semi-autonomously because real-time driving from Earth is impractical. The speed of light creates friction at interplanetary distances, but it remains workable. The delays are minutes or hours, not centuries. Step outside the solar system, and the arithmetic changes completely. The nearest star to our Sun is Proxima Centauri, a dim red dwarf roughly 4.24 light-years away. That distance means light, travelling at its absolute maximum, takes 4 years and nearly 3 months to make the journey. A radio signal sent from Earth right now would arrive at Proxima Centauri in the year 2030. If someone there immediately replied, we would receive the response around 2038, an 8.5-year round trip to the closest star in the galaxy, and Proxima Centauri is exceptionally close by galactic standards. It is our next-door neighbour in a city 100,000 light-years across. Move to more typical stellar distances and the numbers become savage. The bright star Vega lies about 25 light-years away. A message and reply takes 50 years, barely within a single human lifetime, but already long enough that the person who sent the original message might be dead before the answer arrives. The star Betelgeuse, the red supergiant marking Orion's shoulder, sits approximately 700 light-years from Earth. A signal sent to Betelgeuse today would arrive around the year 2726. The reply would reach Earth around the year 3426. 14 centuries of waiting. The entire span from the fall of Rome to the present day compressed into a single exchange. These are still local distances by galactic standards. The centre of the Milky Way lies roughly 26,000 light-years from Earth. The far side of the galactic disk is approximately 75,000 light-years beyond that. Stars exist in every direction, at distances measured in thousands, tens of thousands, and hundreds of thousands of light-years. Every one of those distances represents a one-way travel time for light, the fastest possible signal measured in millennia. But numbers alone cannot make you feel what these distances mean. The human brain evolved to navigate savannas and river valleys. It has no wiring for interstellar scales. To truly grasp the emptiness between stars, we need to shrink the galaxy down to something the body can comprehend. Imagine reducing the sun to the size of a grain of sand. A single grain roughly 0.5 millimeter across, sitting on your kitchen table. At this scale, the Earth would be a speck of dust orbiting that grain at a distance of about 2 inches. Jupiter would be a slightly larger mote circling 10 inches away. The entire solar system out to Neptune's orbit would fit inside a circle about 10 feet across. That sounds manageable. A small bedroom. You could walk across the whole solar system in a few strides. Now find Proxima Centauri at this scale. That next grain of sand, the nearest star, sits 9 miles away. Not 9 inches, not 9 feet, miles. You could place our solar system on a table in downtown Manhattan, drive through the entire borough of Brooklyn, keep going through Queens, cross into Nassau County, and still not reach the nearest star. Between your grain of sand and that distant one lies nothing. No other grains, no other specks, just miles of empty table stretching in every direction. This is what space between stars actually looks like. Not the crowded star fields of science fiction, where ships hop between systems like taxis between city blocks. The real galaxy is almost entirely void. Matter is the exception. Emptiness is the rule, and the emptiness is so vast that even at the scale where stars become grains of sand, the distances between them are measured in miles. Now extend this model to the full galaxy. At our grain of sand scale, the Milky Way would be a disk roughly 210,000 miles across, more than 8 times the circumference of the real Earth. Driving at highway speed without stopping, crossing the model galaxy would take roughly 4.5 months, and within that disk, the 400 billion grains of sand would be separated by average distances of several miles each. The galaxy is not a dense cloud of stars. It is an ocean of nothingness, with occasional tiny islands of matter scattered through it at intervals that dwarf anything in human experience. This emptiness is not incidental to the problem of interstellar contact. It is the problem. Every signal, every probe, every photon that one civilization sends toward another must cross this void. And the void does not merely separate, it dilutes. It weakens. It stretches every attempt at connection until it becomes functionally invisible. Now consider what this means for any civilization trying to make contact with another. Imagine a civilization orbiting a star 5,000 light-years away. They develop radio technology and begin broadcasting a powerful signal in all directions. That signal races outward at the speed of light, expanding as a sphere of electromagnetic radiation. After 1 year, the signal has travelled 1 light-year. After 100 years, 100 light-years. After 5,000 years, the signal finally reaches Earth. But what was Earth doing 5,000 years ago? The Great Pyramid at Giza had not yet been built. Writing had only recently been invented in Mesopotamia. No one on Earth could have detected a radio signal because radio technology would not exist for another 49 centuries. The signal would have washed over our planet and continued outward into space. Unheard, unnoticed, irretrievable. Now reverse the scenario. Humanity began broadcasting radio signals in the early 20th century. Those signals have been expanding outward at the speed of light for roughly 125 years. That means our radio bubble, the sphere of space within which Earth's electromagnetic emissions could theoretically be detected, has a radius of about 125 light-years. That sounds impressive until you compare it to the galaxy. The Milky Way contains approximately 400 billion stars. Within 125 light-years of Earth, there are roughly 10,000 stars. Our radio bubble encompasses approximately 0.0000025% of the galaxy's stellar population. Functionally, our signal has reached nobody. And here is the critical detail that transforms this from a difficulty into something approaching an impossibility. Those signals weaken with distance according to the inverse square law. Double the distance, and the signal strength drops to 1/4. Triple the distance, and it falls to 1/9. By the time Earth's television broadcasts and military radar pulses reach even the nearest stars, they have become extraordinarily faint. At distances of a few dozen light-years, they fall below the detection threshold of any technology currently conceivable, unless the receiving civilization has constructed antenna arrays of almost absurd scale. A study led by researchers at the SETI Institute examined how detectable Earth's own technosignatures would be to an alien civilization using technology comparable to our own. The results were sobering. Earth's strongest continuous signals, such as planetary radar from the Arecibo Observatory before its collapse, could be detected at distances of a few hundred light-years by a receiver equivalent to the square kilometre array. Ordinary radio leakage, television broadcasts, and cellular networks and Wi-Fi would be undetectable beyond roughly 1 light-year. 1 light year. Less than a quarter of the distance to the nearest star, our everyday electromagnetic noise vanishes into the cosmic background almost immediately. This means detection requires intention. For one civilization to notice another, someone has to be deliberately sending powerful targeted signals, and someone else has to be deliberately listening at the right frequency, pointed in the right direction, at the right time. The universe does not make contact easy. It demands that both parties invest enormous resources into bridging a gap that physics makes as wide as possible. But even intention is not enough. Even if both civilizations are actively trying to communicate, they face a problem of alignment so severe that it constitutes a barrier in its own right. Consider how many variables must simultaneously match for a signal to be successfully transmitted and received across interstellar distances. First, frequency. The electromagnetic spectrum is effectively infinite. Radio waves alone span from roughly 3 kHz to 300 GHz, a range covering 11 orders of magnitude. Within that range, a transmitting civilization must choose a specific frequency or narrow band of frequencies on which to broadcast. The receiving civilization must be listening at that same frequency. If the transmitter broadcasts at 1420 MHz, the hydrogen line, and the receiver is scanning at 10 GHz, the signal will be missed completely. Both civilizations must independently converge on the same region of the spectrum. SETI researchers have proposed that certain frequencies are natural meeting points. The hydrogen line at 1420 MHz and the hydroxyl line at 1665 MHz bracket, a region sometimes called the water hole, a quiet zone in the radio spectrum where natural cosmic noise is relatively low. The logic is that any civilization studying astrophysics would recognize these frequencies as universally significant and might choose to transmit or listen there. This is a reasonable guess, but it is still a guess. An alien civilization with different scientific priorities, different atmospheric conditions affecting their local radio environment, or different cultural attitudes toward communication might choose entirely different frequencies. They might transmit in optical wavelengths using powerful lasers. They might use X-rays or gravitational wave modulation, or some encoding method that our current physics does not predict. Every assumption we make about what a signal should look like narrows our search in ways that might exclude the actual signals being sent. Second, direction. Space is three-dimensional. A transmitting civilization aiming a focused beam must choose where to point it. A receiving civilization must choose where to aim its telescope. The galaxy contains hundreds of billions of potential targets. Even a systematic survey that examines one star per second would need thousands of years to check every candidate. And checking each star means spending enough time at each target frequency to detect a signal that might be intermittent, pulsed, or otherwise non-continuous. A brief scan is not sufficient. A thorough scan of a single star across a meaningful frequency range can take hours or days. Multiplied by billions of targets, the time required exceeds civilizational lifespans. Third, timing. A signal might not be continuous. A civilization might broadcast impulses, sweeping its beam across different targets on a rotating schedule. If a receiver happens to be pointed at the right star, at the right frequency, but during a gap between pulses, the signal is missed. This temporal mismatch adds yet another layer of improbability to an already improbable alignment. Fourth, encoding. Even if the frequency, direction, and timing all align, the receiver must be able to recognize the signal as artificial. A continuous carrier wave at a single frequency is the easiest to distinguish from natural sources, but a civilization might encode information in complex modulation patterns that to an unprepared receiver look indistinguishable from noise. The signal might be compressed, encrypted, or structured in ways that optimize bandwidth efficiency at the cost of obvious artificiality. A sufficiently advanced encoding scheme might be mistaken for natural background radiation by any receiver not specifically designed to detect that particular modulation type. The cumulative probability of all these variables aligning simultaneously is extraordinarily small. Frequency, direction, timing, encoding, signal strength, and receiver sensitivity must all match within narrow tolerances. Miss any single variable, and the signal vanishes into the noise. This is not a matter of building better equipment, though better equipment helps. It is a structural feature of the search space itself. The electromagnetic spectrum is too vast, the sky is too large, and the possible signal types are too numerous for any civilization to cover more than a vanishingly small fraction of the possibilities during its technological lifetime. But even deliberate, high-powered transmission faces the tyranny of distance beyond these alignment challenges. Suppose a civilization invests in a transmission system far beyond anything humanity has built. A beacon radiating focused energy equivalent to the output of a small star, aimed at promising stellar targets across the galaxy. The signal propagates outward at light speed. It might be detectable at distances of thousands of light years. That is a genuine achievement. But the signal still takes thousands of years to arrive. The civilization that sent it might not exist anymore by the time the reply returns, and the civilization that receives it is hearing a voice from the deep past, a message composed by beings who lived and died before the recipient's recorded history began. This is not communication. Communication implies exchange, dialogue, a back-and-forth process where information moves between participants within timeframes that allow response and adaptation. What the speed of light permits between stars separated by thousands of light years is something else entirely. It permits the transmission of monuments, messages that travel so slowly relative to civilizational lifespans that they function more like archaeological artifacts than conversations. Receiving such a signal would be among the most profound events in a civilization's history, but it would not be contact in any meaningful sense. It would be the discovery of a relic from a civilization that might already be dust. Now consider the possibility of physical travel rather than electromagnetic signaling. If communication at light speed is too slow, perhaps civilizations could build spacecraft and cross the void in person, closing the gap that signals cannot meaningfully bridge. The physics of interstellar travel is even less forgiving than the physics of interstellar communication. The fundamental problem is energy. Moving any object with mass to a significant fraction of the speed of light requires quantities of energy that escalate exponentially. The rocket equation, first formulated by Konstantin Tsiolkovsky in 1903, describes this escalation with mathematical precision. To accelerate a spacecraft, you need fuel, but the fuel itself has mass, which must also be accelerated, which requires more fuel, which adds more mass. This recursive relationship means that the fuel requirement grows exponentially with the desired velocity. Consider the numbers. To accelerate a spacecraft, the mass of a small car to 10% of the speed of light, roughly 30,000 kilometers per second, using the most efficient chemical rockets available today, you would need a fuel mass greater than the mass of the observable universe. This is not an engineering challenge. It is a physical impossibility for chemical propulsion at interstellar scales. Nuclear propulsion improves the situation but does not solve it. Fusion reactions convert mass into energy roughly 100 times more efficiently than chemical combustion. A fusion-powered spacecraft could theoretically achieve velocities of a few percent of light speed, but the fuel mass required remains enormous, thousands of times the mass of the payload for even modest interstellar distances. And fusion propulsion at this scale remains entirely theoretical. No fusion engine has ever been built, let alone one capable of sustained thrust over years or decades. Antimatter propulsion represents the theoretical maximum of energy extraction from mass. When matter and antimatter annihilate, they convert their entire combined mass into energy according to Einstein's famous equation. A kilogram of antimatter reacting with a kilogram of normal matter releases roughly 43 megatons of explosive energy. In principle, antimatter rockets could approach significant fractions of light speed. In practice, humanity produces approximately 10 nanograms of antimatter per year at a cost of roughly $62 trillion per gram. Scaling antimatter production to the quantities needed for interstellar travel would require energy expenditures exceeding the total output of human civilization by many orders of magnitude. Even exotic propulsion concepts face crushing limitations. Solar sails and laser-driven light sails like those proposed by the Breakthrough Starshot Initiative, could potentially accelerate ultra-lightweight probes, gram-scale craft carrying miniature instruments, to perhaps 20% of light speed, using ground-based laser arrays generating 100 gigawatts of focused power. At that velocity, a probe could reach Alpha Centauri in approximately 20 years, but such a probe could carry no crew, no life support, and no ability to decelerate on arrival. It would streak through the target star system in a matter of hours, snapping photographs and transmitting data back to Earth during a brief flyby. This is reconnaissance, not travel. And even this modest concept remains far beyond current engineering capability. The Breakthrough Starshot project, proposed in 2016, has made limited progress toward building the required laser infrastructure. For any spacecraft carrying living passengers or heavy equipment, the velocity limitations become crippling. A ship traveling at 1% of the speed of light, roughly 3,000 kilometers per second, an achievement far beyond any technology currently demonstrated, would take 424 years to reach Proxima Centauri. A journey to a star 1,000 light-years away would take 100,000 years. To a star 10,000 light-years away, 1 million years. These are not travel times, they are geological epochs. Mountains erode in less time. Species evolve and go extinct in less time. No known material can maintain structural integrity over such durations. No life support system can sustain a biological crew for centuries or millennia. No social structure has ever survived intact for even a fraction of these intervals. Generation ships, hypothetical vessels designed to sustain entire human communities across centuries-long voyages, remain a staple of science fiction but face problems that no one has solved even theoretically. Maintaining a closed ecosystem capable of recycling air, water and food for hundreds of years without catastrophic failure requires engineering reliability far beyond anything humanity has achieved. The social dynamics of a small community confined to a vessel for dozens of generations, with no possibility of outside contact or resupply, present psychological and sociological challenges that are entirely unprecedented. The genetic consequences of a small breeding population isolated for centuries include inbreeding depression and loss of genetic diversity, both of which threaten long-term viability. Every proposed solution to these problems introduces new complications. Larger ships require more energy to accelerate. Cryogenic suspension of passengers remains entirely fictional. Artificial intelligence capable of managing a ship for centuries without human oversight does not exist and may never exist in a reliable form. The conclusion is stark. Under known physics, interstellar travel by biological beings is not merely difficult. It is so energy-intensive, so time-consuming, and so technically demanding that no civilization, regardless of its advancement, can treat it as a routine activity. Individual missions to nearby stars might be conceivable for a sufficiently advanced and motivated civilization, but galaxy-spanning travel, the kind that would be required for civilizations separated by thousands or tens of thousands of light-years to physically meet, is effectively ruled out by the basic structure of physics. This leaves electromagnetic communication as the only plausible means of contact between distant civilizations. And as we have already seen, communication at light speed across galactic distances is not really communication at all. It is the transmission of time capsules between civilizations that may never overlap in their active periods. Here is where we need to introduce a concept that makes the isolation quantifiable. Think of every civilization as sitting at the center of what we might call a contact sphere. This sphere represents the volume of space within which that civilization can meaningfully send and receive signals during its technological lifetime. The radius of the contact sphere is determined by half the civilization's active lifespan, because a signal must travel outward and a reply must travel back within the window, during which the civilization remains functional. If a civilization broadcasts for 10,000 years, the maximum distance at which it can complete a single exchange is 5,000 light-years. Its contact sphere has a radius of 5,000 light-years. That sounds large. 5,000 light-years encompasses millions of stars. but the Milky Way's disk has a radius of approximately 50,000 light-years. A contact sphere of 5,000 light-years covers a circle that represents roughly 1% of the galaxy's total disk area. And that assumes the civilization sustains its technological capability for 10,000 years without interruption, an assumption that has no supporting precedent from any known civilization. If the civilization's technological lifespan is shorter, the contact sphere shrinks dramatically. A civilization that lasts 1,000 years has a contact sphere with a radius of 500 light-years, covering roughly 1/10,000th of the galactic disk. A civilization that lasts 500 years, closer to the historical average for human political entities, has a contact sphere of 250 light-years, encompassing a vanishingly small fraction of galactic space. Even the largest plausible contact sphere covers only a tiny portion of the galaxy. And within that sphere, contact requires not just proximity, but simultaneity. The other civilization must be active, broadcasting, and listening during the same narrow window. Two civilizations with overlapping contact spheres but non-overlapping active periods will never detect each other. Their signals will pass through space where the other once existed or will someday exist, arriving too early or too late to be received by anyone. The galaxy is not a room where civilizations can shout and expect to be heard. It is a vast, dark ocean where each civilization lights a brief candle. The candle illuminates a tiny patch of darkness for a cosmically insignificant moment. Then it goes out. Another candle lights up somewhere else, thousands of light years away, thousands of years later. It illuminates its own tiny patch. Then it also goes out. Neither candle ever knows the other existed. Both burn in what appears to be total darkness. This is what the speed of light does to the dream of interstellar contact. It does not merely make contact difficult, it imposes a hard geometric limit on how far any civilization's influence can reach during its lifetime. And that limit, for any civilization with a plausible lifespan, is a tiny fraction of the galaxy. The speed of light is often described as fast, and it is, by human standards. A photon can circle the Earth 7 times in a single second. But the galaxy is not built to human standards. The galaxy is built on a scale where even light is slow. A photon leaving one edge of the Milky Way will not reach the other edge for 100,000 years. In that time, entire species can evolve and go extinct. Stars can be born, live through their main sequence, and die as white dwarfs. Civilizations can rise, flourish, and vanish without a trace. The speed of light is fast enough to illuminate the cosmos. It is far too slow to connect it. And this is only the first wall. We have established that distance and the speed of light impose a hard limit on how far any civilization can reach. We have shown that interstellar travel under known physics is effectively impossible at galactic scales. We have demonstrated that even light-speed communication reduces to the exchange of archaeological relics between civilizations separated by centuries or millennia. And we have seen that even when a signal is sent with all the power and intention a civilization can muster, the alignment problem frequency, direction, timing, encoding makes detection an exercise in finding a single specific grain of sand on a beach the size of a continent. But there is something worse waiting behind this wall, because even if two civilizations happen to exist close enough for their contact spheres to overlap, even if they are among the cosmically fortunate few whose candles burn at the same time in the same neighborhood, the speed of light still sabotages them, not through distance alone, but through what distance does to the very nature of exchange. The lag between sending and receiving does not merely slow conversation, it destroys it. It turns dialogue into monologue. It transforms the dream of meeting another mind into the reality of shouting into a void and hoping that someone, somewhere, thousands of years from now, might hear the echo. That is the second wall. And it is worse than the first, because the first wall tells you that most civilizations are too far apart to ever interact. The second wall tells you that even the ones close enough to try will find that the interaction is hollow, a pale ghost of what contact was supposed to mean. The distance has been measured. The speed limit has been confirmed. The prison has walls that no technology can breach. But the true cruelty of the cosmos is not the walls themselves. It is what happens to the civilizations trapped inside them when they try, with everything they have, to reach through the bars. Suppose, against all odds, it works. Suppose a civilization 1500 light years from Earth builds a transmitter powerful enough to punch a signal across the void. Suppose they aim it in our direction. Suppose the signal is structured in a way that is recognizably artificial, a repeating mathematical sequence, a narrowband pulse at a frequency that nature does not produce, something that screams deliberate origin. And suppose we detect it. Suppose one of our radio telescopes, scanning the sky as part of a SETI survey, picks up the signal and confirms that it is not terrestrial interference, not a pulsar, not a quasar, but genuine evidence of an intelligence that arose around a distant star. This would be the most important discovery in the history of science. It would confirm that life and intelligence are not unique to Earth. It would reshape philosophy, religion, and the human understanding of our place in the cosmos. Headlines would circle the globe, governments would convene, the species would, for a brief and extraordinary moment, feel less alone, and then reality would set in. The signal we detected left its source 1500 years ago. When those beings composed their message, the Roman Empire was still standing. Muhammad had not yet been born. The entire medieval period, the Renaissance, the Scientific Revolution, the Industrial Revolution, both world wars, the invention of computers, the moon landing, and the creation of the internet all occurred during the time that signal was traveling through space. The civilization that sent it experienced none of these events. They have no knowledge of us. They do not know Earth exists. They were speaking into the dark, exactly as we would be if we transmitted a reply. Now imagine we do reply. We compose a response, encode it in a powerful transmission, and aim it toward the star system from which the original signal came. Our reply leaves Earth at the speed of light. It will arrive at its destination in 1500 years. If the civilization that sent the original message still exists, and if they are still listening, they will receive our response 3,000 years after they sent their initial transmission. 3,000 years. The entire span of recorded Western history fits inside that pause. But the word response is misleading. By the time our reply arrives, the beings who wrote the original message are long dead. Their grandchildren are dead. Hundreds of generations have passed. Their civilization may have transformed beyond recognition, collapsed, or gone extinct. The response they receive, if anyone is there to receive it, addresses questions no one remembers asking. It references a context that no longer exists. It arrives not as an answer, but as a voice from the deep past of another world, as disconnected from the current moment as a Sumerian clay tablet is from a modern text message. This is what communication lag does to interstellar exchange. It does not merely slow the conversation, it eliminates the conversation entirely. What remains is something fundamentally different from what the word contact implies to a human mind. There is no dialogue. There is no negotiation. There is no shared experience unfolding in real time. There is only the exchange of monologues across a temporal chasm so wide that neither participant can meaningfully affect the other. Consider what conversation actually requires. Two minds must be able to share a common reference frame. They must respond to each other's statements within a window short enough that both parties remember and care about the topic under discussion. A conversation where each reply takes minutes is challenging but functional. Diplomats and military commanders have managed it for centuries using messengers on horseback. A conversation where each reply takes hours is strained but possible. Mission controllers at NASA manage this with Mars rovers every day. A conversation where each reply takes years begins to break down. Only the most patient institutions, ones operating on generational timescales, could sustain it. A conversation where each reply takes centuries is not a conversation at all. It is correspondence between civilizations that might as well exist in different epochs of history. And 1500 light-years is close by galactic standards. The average distance between civilizations in a galaxy containing 10,000 active cultures is roughly 1700 light-years. For a galaxy with only a few hundred active civilizations, a number many estimates suggest is more realistic. The average separation stretches to tens of thousands of light years. At those distances, the round-trip communication time exceeds the entire duration of recorded human civilization by orders of magnitude. Some theorists have proposed that civilizations might sustain multi-generational communication projects, institutions specifically designed to maintain a dialogue across centuries or millennia. The idea has a certain nobility to it. A civilization that commits to a conversation lasting thousands of years, faithfully transmitting and receiving across generations, preserving context and continuity through every political upheaval and cultural transformation that occurs during the wait. But no institution in human history has achieved anything remotely comparable. The oldest continuously operating organizations on Earth, certain religious orders and universities, span roughly 1,000 years. None of them have maintained a single, specific, technical project across that entire duration. The idea that a civilization would sustain a precise, technically demanding, multi-millennial communication effort without interruption, maintaining both the physical infrastructure and the cultural commitment across hundreds of generations, has no precedent anywhere in the human experience. It is not impossible in principle, but assuming it as a default expectation is profoundly unrealistic. And this assumes both civilizations survive the entire exchange. A 3,000-year round trip requires both participants to remain technologically active and interested for the full duration. If either civilization experiences a dark age, a catastrophic war, a resource crisis, or an extinction event during that window, the chain breaks. The reply arrives at an empty world. The conversation was never a conversation. It was a message in a bottle thrown into an ocean where the intended recipient drowned before it washed ashore. The communication lag problem alone is devastating. But it is not the worst barrier civilizations face. There is a third wall, and it is the one that transforms the silence of the cosmos from a puzzle into something approaching a verdict. It is the overlap problem, and understanding it requires thinking about time on a scale that human intuition was never designed to grasp. The Milky Way galaxy is approximately 13.6 billion years old. The first stars ignited within a few 100 million years of the Big Bang, and conditions suitable for rocky planet formation likely existed within the first 2 to 3 billion years. If we conservatively estimate that habitable planets have existed in the galaxy for roughly 10 billion years, then the window during which civilizations could potentially arise stretches across an almost incomprehensible span of cosmic history. Now consider how long a civilization remains detectable. This is the L factor from the Drake equation, the variable that dominates every calculation about interstellar contact. Estimates for L vary wildly. Pessimists, pointing to the brevity of human technological civilization and the many existential risks we face, suggest values of a few hundred years. Moderates propose a few thousand to a few tens of thousands of years. Optimists imagine civilizations that endure for millions or even billions of years. Let us be generous. Let us assume a civilization's detectable technological phase lasts 10,000 years. This is already far longer than any human civilization has maintained a consistent technological trajectory. It assumes a culture that avoids nuclear self-destruction, ecological collapse, artificial intelligence catastrophe, asteroid impact, and every other existential threat for 100 centuries without interruption. 10,000 years is an optimistic number, but grant it for the sake of argument. 10,000 years sounds like a long time. It is not. Not against the backdrop of galactic history. 10,000 years is 1/1,000,000th of the galaxy's age. If the Milky Way's 13.6 billion year history were compressed into a single calendar year, 10,000 years would occupy less than 24 seconds. A civilization that lasts 10,000 years flickers into existence for the duration of a single heartbeat in cosmic time, broadcasts its signals, searches for companions, and then goes dark. Whether it ends through catastrophe, transformation, or simply the natural exhaustion of a technological phase, it vanishes from the electromagnetic landscape of the galaxy in what amounts to an instant. Now imagine a second civilization arising in the same galaxy, also lasting 10,000 years. What are the chances that these two civilizations are active at the same time? If both civilizations appear randomly within the galaxy's 10 billion year habitable window, the probability that their 10,000-year active periods overlap is approximately 1 in 500,000. Two heartbeats occurring randomly within a year-long span. The odds that they happen to beat simultaneously are vanishingly small. But temporal overlap is necessary and not sufficient for contact. The two civilizations must also be close enough for signals to travel between them within their shared active window. If they are 5,000 light-years apart, the fastest possible exchange takes 10,000 years. That means their active periods must not only overlap, they must overlap by at least 10,000 years, enough time for a signal to make the full round trip. For civilizations lasting only 10,000 years each, this requires nearly perfect temporal alignment. They must switch on their transmitters within a few thousand years of each other, an alignment that becomes progressively less likely as the required overlap window grows. Combine the temporal requirement with the spatial requirement, and the probability of contact between any two randomly placed, randomly timed civilizations drops to levels that are difficult to distinguish from zero. This is the overlap problem. It is not about whether civilizations exist, it is about whether they coexist. The galaxy could produce 1 million civilizations across its history, each one lasting 10,000 years, and the overwhelming majority of them would never share the sky with another active culture within signal range. Each civilization would rise, search the heavens, find nothing, and conclude that it was alone. Not because the galaxy was empty, but because the galaxy was empty right now, in their neighborhood, during their brief moment of wakefulness. To make this concrete, consider a simple model. Suppose the galaxy produces one new civilization every 10,000 years. On average, somewhere within its habitable zone. Over 10 billion years, that yields 1 million total civilizations. An impressive number, but at any given moment, only one civilization is active. Each one occupies its 10,000-year window in solitude, separated from its nearest temporal neighbor by a gap of 10,000 years, during which no one is broadcasting, no one is listening, and the galaxy is functionally silent. Now increase the rate. Suppose a new civilization appears every 1,000 years. Over 10 billion years, this produces 10 million civilizations. At any given moment, roughly 10 are active simultaneously. 10 civilizations scattered across a galaxy 100,000 light-years wide. The average distance between them is approximately 30,000 light-years. A signal from one would take 30,000 years to reach another, but each civilization only lasts 10,000 years. The signal arrives 20,000 years after the sender has gone silent. The recipient never existed when the signal was sent. Nobody hears anything. Increase the rate further. One new civilization every 100 years. 100 million civilizations across galactic history. At any given moment, approximately 100 are active. The average separation drops to roughly 10,000 light-years. The round-trip signal time is 20,000 years. Each civilization lasts 10,000 years. The signal still arrives after the sender is gone. The overlap is still insufficient for exchange. Only when you push the numbers to extremes does contact become plausible. If the galaxy produces a new civilization every 10 years, and each lasts 100,000 years, then roughly 10,000 civilizations exist simultaneously, separated by average distances of about 1,700 light-years, with round-trip signal times of 3,400 years, well within their active windows. Under these conditions, contact is possible in principle, but these numbers require both an extraordinarily high rate of civilizational emergence and an extraordinarily long civilizational lifespan. Both assumptions are far more optimistic than any evidence supports. The rate of one civilization every 10 years implies that a new technological species emerges somewhere in the galaxy, roughly once a decade, continuously, for 10 billion years. Given the evolutionary timescales required for intelligence to develop, the rarity of the conditions necessary, and the fact that Earth is the only known example, this rate seems implausibly high. And a 100,000-year technological lifespan assumes a civilization that endures 10 times longer than modern humans have existed as a species, maintaining a continuous technological infrastructure throughout, without a single interruption sufficient to end its detectable phase. The overlap problem is not just a quantitative challenge, it reveals a qualitative truth about the structure of cosmic time. Civilizations are not permanent features of the galaxy. They are events, brief flares of technological activity that appear, persist for a geologically insignificant moment, and then subside. The galaxy does not accumulate civilizations the way a city accumulates buildings. It experiences them the way a forest experiences. Lightning strikes, brief, intense, separated by long intervals of silence. Each strike illuminates a tiny area for a moment before the darkness returns. This realization strikes at the heart of the assumption we identified at the beginning, the belief that enough civilizations must eventually lead to contact. That belief treats civilizations as though they are permanent dots on a map, sitting in fixed positions, waiting to be connected by lines of communication. But civilizations are not dots on a map. They are sparks in a rainstorm. Each one flares for an instant against an immense background of time and space. The rain continues before and after. The sparks do not know about each other because they do not coexist. But the overlap problem has a dimension we have not yet examined. Even in the rare scenario where two civilizations do happen to share the same era, close enough in space for signals to bridge the gap within their overlapping lifetimes, there remains a compounding barrier that could still prevent detection. Call it the technological alignment problem. A civilization searching for technosignatures must make assumptions about what those signatures look like. Those assumptions are inevitably shaped by the searcher's own technology, scientific history, and cultural priorities. Humanity searches primarily in the radio spectrum, because radio was the first technology we developed that could plausibly be detected across interstellar distances. We search secondarily in optical wavelengths because lasers represent our other high-energy focused transmission capability. We assume that an alien signal will be structured in ways we can recognize. Narrowband carriers, repeating patterns, mathematical sequences, or other features distinguishable from natural astrophysical noise. But another civilization, one that developed along a different technological trajectory, might not use radio at all. They might have bypassed radio communication entirely, moving directly from chemical signaling to optical networks to some form of directed energy transmission that operates in a part of the spectrum we do not routinely monitor. A species that evolved with different sensory organs might find X-ray or ultraviolet frequencies as natural as radio feels to us. A civilization that prioritized computation over communication might encode its transmissions in ways optimized for information density rather than detectability, producing signals that look like noise to any receiver not designed to decode that specific protocol. This is not speculation. It is a direct consequence of the diversity of possible evolutionary and technological pathways. There is no universal law that says all technological civilizations converge on the same communication methods. Radio is not cosmically special. It is humanly special, because it happens to be what we invented first. An alien civilization might regard our radio searches the way we would regard someone scanning the ocean for smoke signals while ignoring satellite transmissions passing overhead. They are searching, but they are searching in the wrong medium. The SETI community is aware of this limitation. Recent years have seen expansion into optical SETI, infrared surveys, and even preliminary investigations of neutrino and gravitational wave detection as potential technosignature channels. The European Southern Observatory has discussed plans for optical SETI programs using next-generation telescopes expected to operate in the 2040s. Each new search modality opens a previously invisible window, but each window also represents a guess about alien technology. And every guess could be wrong. The technological alignment problem compounds the overlap problem in a devastating way. It is not enough for two civilizations to exist at the same time and close enough for signals to travel between them. They must also be searching for the same type of signal. If civilization A broadcasts radio and civilization B listens only in optical, they will miss each other completely, even if they occupy the same region of space during the same era. They are ships passing not just in the night, but on different oceans entirely. Multiply the temporal overlap probability by the frequency alignment probability by the modulation compatibility probability, and the chances of two civilizations successfully detecting each other shrink further with each additional variable. The universe does not merely separate civilizations in space and time, it separates them in methodology, in technology, in the very language they use to shout into the void. Recent scientific work has attempted to formalize some of these combined problems. Remember the Nottingham estimate from earlier, the study that calculated approximately 36 active civilizations in the Milky Way at any given time. We already saw that this number produces average separations of 17,000 light-years and round-trip signal times of 34,000 years. But those figures only measure distance. The overlap problem adds a second filter on top of the spatial one. Even if 36 civilizations exist simultaneously right now, they almost certainly did not switch on their transmitters at the same moment. Some may have been broadcasting for 8,000 years already. Others may not begin for another 5,000. The windows are scattered randomly across time. For any two of those 36 civilizations to exchange even a single signal, their active periods must overlap by enough millennia to cover the round-trip light travel time between them. At 17,000 light-years apart, that requires an overlap of at least 34,000 years. For civilizations lasting only 10,000 years, that overlap is physically impossible. The distance alone was already fatal. The timing makes it certain. Other estimates are even less encouraging. A Bayesian analysis by researchers at the Future of Humanity Institute at the University of Oxford, incorporating the observed absence of technosignatures despite decades of searching, concluded that the expected number of active civilizations in the galaxy could be far less than one. This does not mean civilizations never arise. It means they arise so rarely or persist so briefly that at any given moment, the galaxy is likely empty of anyone detectable. The silence we observe through our radio telescopes is not a mystery to be solved. It may simply be the expected state of a galaxy, where civilizations bloom and fade in temporal isolation. The Breakthrough Listen initiative, the most comprehensive SETI program ever conducted, has surveyed over 2,000 nearby stars and scanned the galactic plane across billions of radio channels since its inception in 2015. Using the Green Bank telescope, the Parkes Observatory, and the Meerkat Array, the project has achieved sensitivities capable of detecting powerful transmitters at distances of thousands of light-years. AI-driven signal processing, developed in 2025, has accelerated analysis by a factor of 600, while reducing false positives tenfold. The project has scanned interstellar objects, including 3I Atlas, the third confirmed interstellar visitor to our solar system. No technosignatures have been detected. Not one confirmed artificial signal in any survey, at any frequency from any direction. Meanwhile, NASA chartered a technosignatures science analysis group in 2024, tasked with integrating the search for technological life into NASA's broader exoplanet and astrobiology research portfolio. The group, expected to report by 2026, represents an institutional acknowledgement that the search for intelligent life should be a formal component of space science, rather than a fringe pursuit. This is progress, but it also underscores how early we remain in the search. We have sampled a minuscule fraction of the galaxy's stars, across a tiny range of possible signal types, during an extremely brief window of observation. The absence of detection so far could mean we are alone. It could equally mean we have barely begun to look. But the overlap problem suggests something more unsettling than either of those possibilities. It suggests that even a perfect search, one that scanned every star in the galaxy at every frequency simultaneously, might still find nothing. Not because civilizations are absent from galactic history, but because none of them happen to be active right now within our detection range. The galaxy could be populated with the residue of 1,000 extinct civilizations, their planets still orbiting, their ruins still standing, their last transmissions still racing through space, long after the transmitters fell silent. We would see none of it. Dead civilizations do not broadcast. Their signals, if they ever sent any, passed through our region of space millennia before we existed, or will arrive millennia after we are gone. And this leads to one of the most haunting implications of the entire argument. Right now, at this very moment, the galaxy may be threaded with ghost signals. Transmissions launched by civilizations that no longer exist, still propagating outward through interstellar space at the speed of light, carrying messages from minds that burned and faded millions of years ago. These signals are real. They are physical. They are electromagnetic radiation obeying the same laws as starlight and cosmic background radiation. They carry information encoded by beings who wanted to be heard, and they are passing through star systems where no one is listening. Some of those ghost signals may have already passed through our solar system. They arrived before Earth had multicellular life, or before mammals evolved, or before primates descended from the trees. They washed over a world that had no instruments, no curiosity, no capacity to receive them. They continued outward, carrying their messages deeper into the galaxy, growing fainter with every light year until they fell below the noise floor of the cosmos and became indistinguishable from the random hiss of the universe itself. Other ghost signals are on their way to us now. Somewhere in the galaxy, a civilization that went extinct 3,000 years ago transmitted a powerful beacon during its final centuries. That beacon has been traveling through space ever since. It has already passed through hundreds of star systems, none of which harbored a technological species at the time. In 2,000 years, it will reach Earth, but by then, humanity may have gone silent itself. Our radio telescopes may be ruins. Our species may have evolved, migrated, or vanished. The signal will arrive at a world that cannot hear it, just as all the signals before it arrived at worlds that could not hear them. The galaxy is full of these phantom messages. Every civilization that ever broadcast left behind an expanding shell of electromagnetic radiation moving outward at light speed. Those shells still exist. They are still expanding. They are passing through the galaxy right now, carrying voices from the dead across distances the living will never cross. Some of these shells intersect with each other in space, two ghost signals passing through the same region of vacuum, an accidental meeting of messages from civilizations that never met. Neither sender knew the other existed. Neither message has a recipient. They are letters addressed to no one, written by species that are gone, traveling through a darkness that does not care. This is the temporal desert, the vast stretches of empty time that separate one civilization's active period from another's in any given region of space. Even in a galaxy that produces civilizations regularly, the temporal desert dominates the landscape. A region of space might host a civilization for 10,000 years, then sit empty for 10 million years before another arises nearby. During those 10 million years of silence, the region appears dead. Any civilization in a neighboring region that happens to look in that direction during the gap sees nothing. The evidence of past habitation has faded. The evidence of future habitation has not yet appeared. The observer concludes, reasonably but incorrectly, that this patch of the galaxy has never produced and will never produce intelligent life. Now multiply this across the entire galaxy. Millions of regions, each experiencing their own intermittent flickers of civilizational activity, separated by immense temporal gaps. At any given moment, a handful of these regions are active, the rest are dark. The active regions are scattered across the galactic disk, separated by thousands or tens of thousands of light years. Each active civilization looks outward and sees only darkness, not because the other active civilizations do not exist, but because they are too far away for their signals to have arrived yet, or because the light travel time means the observer is seeing those distant regions as they were thousands of years ago, before or after the civilizations that were active. Every civilization peers through a temporal keyhole. It sees the galaxy not as it is, but as it was at various points in the past, with the depth of the past increasing with distance. A civilization observing a star 1,000 light years away sees that star as it was 1,000 years ago. If a neighboring civilization occupied that system but went extinct 500 years ago, the observer would still see the system as inhabited for another 500 years, until the light from the extinction event finally arrives. Conversely, if a civilization has just arisen around a star 3,000 light-years away, no one will know about it for 3,000 years. The galaxy is a patchwork of temporal snapshots, each one showing a different moment in history, and no observer can see the present state of any region beyond its own immediate neighborhood. This means the galaxy that each civilization observes is not the galaxy that actually exists. It is a composite of outdated information, a mosaic of past states stitched together by the finite speed of light. The real galaxy, the one that exists right now in its totality, is invisible to everyone. No civilization sees the truth. Every civilization sees a version of the galaxy that is centuries, millennia, or millions of years out of date, depending on where it looks. And it is within this fog of temporal distortion that civilizations must search for each other. They must send signals into regions whose current state they cannot know. They must listen for signals from civilizations whose existence they cannot confirm. They must hope that somewhere in the galaxy, another mind is doing the same thing at the same time, close enough for the signals to bridge the gap before both participants go dark. And they must hope that the other mind is using a technology they can recognize, searching in a spectrum they monitor, encoding information in a way they can decode. Every additional variable reduces the odds. Every assumption narrows the keyhole further. The first wall was distance. The sheer physical separation between stars makes most of the galaxy permanently unreachable. The second wall was communication lag. Even across bridgeable distances, the delay between sending and receiving destroys the possibility of meaningful exchange. The third wall is timing. Civilizations do not persist long enough to wait for the slow machinery of light-speed communication to connect them across typical galactic separations. And compounding all three walls is the alignment problem. Even civilizations that beat the odds of distance, lag, and timing may still miss each other because they searched in different spectra, used different encodings, and pointed their instruments in different directions at different times. Together, these barriers do not merely make contact unlikely, they make isolation the default outcome for any civilization that arises in the Milky Way. Not because the galaxy is hostile, not because some great filter destroys civilizations before they can reach out, but because the basic geometry of space, the fundamental speed limit of information transfer, the brevity of civilizational lifespans relative to cosmic time, and the vast diversity of possible technological approaches conspire to ensure that minds arising in different places and different eras will almost never share the same moment. The galaxy may have produced civilizations before us. It may produce them after us. Somewhere across its 100,000 light-year expanse, another species might be staring at the same stars we see, asking the same questions, feeling the same hope, but they are not hearing us. And we are not hearing them. Not because our instruments are too weak, not because our searches are too narrow, but because the universe made the stage wider than light can cross, the script longer than any actor's part, and the scenes separated by intermissions that last longer than civilizations survive. What remains now is to confront what this means, not just for the search for extraterrestrial intelligence, not just for the Drake equation or the Fermi paradox, but for us, for what it means to be a conscious species in a universe that may be full of conscious species, none of whom will ever know the others existed. We have now seen the architecture of cosmic isolation. 3 walls, each one sufficient on its own to cripple the dream of interstellar contact, and together forming a barrier that may be absolute. Distance ensures that most civilizations are physically unreachable. The speed of light ensures that even reachable distances impose delays that destroy meaningful exchange. And the overlap problem ensures that civilizations arising at different times in galactic history will almost never share the same window of existence within signal range. Each wall reinforces the others. Each one closes an escape route that the previous wall left open. Together, they do not merely make contact difficult, they make separation the structural default of cosmic life. But stating these barriers as abstract principles does not capture what they actually mean for a civilization living inside them. To feel the full weight of this conclusion, we need to stand inside it. We need to imagine what it is like to be a species that has done everything right, that has built the telescopes, launched the surveys, listened with exquisite patience, and found nothing. Not because the universe is barren, but because the universe is built so that finding is nearly impossible. Begin with what a civilization actually experiences when it looks outward. You develop radio technology. Within a few decades, you begin scanning the sky for artificial signals. You search nearby stars first, then expand to more distant targets. You build larger arrays, more sensitive receivers, better algorithms for distinguishing natural noise from deliberate transmission. You survey thousands of stars, then tens of thousands, then hundreds of thousands. You listen across billions of frequency channels simultaneously. You search for continuous carriers, pulsed beacons, broadband signals, narrowband whispers, laser flashes, infrared anomalies, atmospheric signatures that might indicate industrial activity on distant worlds. You do this for decades, then centuries. You find nothing. At first, the silence is puzzling but not alarming. The galaxy is large. Your search has covered only a tiny fraction of it. Absence of evidence is not evidence of absence. You continue. You improve your instruments. You expand your search radius. You develop artificial intelligence systems capable of analyzing data at speeds no biological mind can match. You scan the galactic plane. You examine globular clusters. You monitor nearby galaxies. You check every interstellar object that passes through your solar system for signs of artificial origin. You find nothing. The silence deepens. Generations of scientists devote their careers to the search. Public interest waxes and wanes. Funding fluctuates. Some voices argue the search is futile, that the resources would be better spent elsewhere. Others insist that the question is too important to abandon. The search continues, sustained by the conviction that in a galaxy containing hundreds of billions of stars and tens of billions of potentially habitable planets, someone else must be out there. But century after century, the sky remains quiet. No repeating signal, no structured pulse, no anomalous atmospheric chemistry on any observed exoplanet that cannot be explained by natural processes. No megastructures dimming distant stars. No probes drifting through your solar system. Nothing. What do you conclude? The obvious conclusion is that you are alone. That life is rare, intelligence is rarer, and technological civilization is a freak occurrence that happened exactly once in the history of the galaxy. This is the conclusion that stares you in the face every time you point a telescope at the sky and hear only static. It is the simplest explanation. It requires no elaborate theory, no hidden variables, no cosmic conspiracy. You are alone because there is no one else. The universe produced one civilization, yours, and when you are gone, the galaxy will return to the silence that preceded you. But this conclusion, while simple, may be wrong. And the reason it may be wrong is everything we have explored so far. The silence you hear is exactly what you would expect to hear, even if the galaxy has produced thousands or millions of civilizations across its history, because those civilizations did not arise at the same time you did. They did not arise within signal range. Their transmissions passed through your region of space before your species evolved, or will arrive after your civilization has ended. The galaxy is not empty. It is desynchronized. The minds are there. They are just never there at the same time. This is a fundamentally different kind of aloneness than the one most people imagine when they think about the Fermi paradox. The conventional framing asks a binary question. Are we alone? Yes or no? And it treats alone as a synonym for unique, the only civilization in the galaxy, the only intelligence the cosmos has ever produced. The answer to that question might be yes, but the more disturbing possibility is that the answer is no, and it does not matter. You are not the only civilization the galaxy has ever produced. You might be one of millions, but you will never know it. You will never detect the others. You will never receive their signals. You will never find their ruins. You will never confirm their existence through any observational means available to you. They lived and died in other places and other times, separated from you by distances that light cannot bridge within your lifetime, and by temporal gaps that ensure your respective windows of activity never overlap. You are not unique, you are isolated, and in practical terms, for everything that matters to a civilization trying to understand its place in the cosmos, isolation is indistinguishable from uniqueness. This is the conclusion that the three walls converge upon. Not that the universe is empty, but that it might as well be. Not that civilizations are rare, but that they are scattered across such immense reaches of space and time that each one experiences the cosmos as though it were the only mind that ever existed. A universe full of voices, none of which can hear each other. A galaxy teeming with intelligence across its history, silent at every moment to every observer. Consider the emotional architecture of this realization. Humanity has spent millennia imagining contact with other minds. Our mythology is filled with gods, spirits, and beings from beyond who visit, communicate, judge, and interact with us. Our science fiction is built almost entirely on the premise that interstellar civilizations can meet, trade, fight, cooperate, and share knowledge. The dream of contact is not a peripheral curiosity. It is one of the deepest yearnings of conscious life. The desire to know that the universe is not indifferent, that intelligence is not a local accident, that somewhere out there, another mind is looking back. The three walls do not deny the existence of those other minds. They deny the meeting. They permit the universe to be rich with intelligence while ensuring that each instance of intelligence experiences total solitude. This is not the comforting loneliness of a traveller who knows that home exists somewhere behind them. This is the loneliness of a traveller who knows that other travellers exist on the same road, but will never encounter any of them because the road is too long, the walking speed too slow, and each traveller's journey too brief. And here is what makes this not merely sad but structurally tragic. The very features of the universe that permit life to arise are the same features that prevent life from connecting. Stars must be separated by light years to avoid gravitational disruption. If stars were packed close together, their mutual gravitational interactions would destabilize planetary orbits, strip atmospheres, and prevent the long-term stability necessary for biological evolution. The emptiness between stars is not a flaw in the universe's design. It is a prerequisite for life's existence. The distances that isolate civilizations are the same distances that allowed those civilizations to develop in the first place. Similarly, the speed of light is not an arbitrary limitation. It is a consequence of the structure of space-time, bound up with causality itself. If information could travel faster than light, the logical structure of cause and effect would break down. Events could influence their own pasts. The temporal ordering that allows coherent physical processes, including the chemistry that underlies biology, would become incoherent. The speed limit that prevents civilizations from communicating across galactic distances is the same speed limit that allows the physics of life to function. You cannot remove the prison bars without collapsing the building they support. And the brevity of civilizational lifespans, the factor that creates the overlap problem, is itself a consequence of the complexity that makes civilizations possible. Complex systems are inherently fragile. The more sophisticated a civilization becomes, the more potential failure modes it accumulates. Technological civilizations depend on energy systems, communication networks, ecological stability, social cohesion, and political structures that are all vulnerable to disruption. Even without self-inflicted catastrophe, the natural evolution of a species and its culture ensures that the technological phase is transient. Species evolve, cultures transform, technologies are abandoned and replaced. The specific configuration that makes a civilization detectable, the phase during which it actively broadcasts electromagnetic signals into space, is inherently temporary. Nothing lasts forever, and the things that make civilizations interesting are the same things that make them brief. The Pacific Ocean is vast, but a Polynesian voyaging canoe could cross it in weeks. The Atlantic is wide, but a European caravel could traverse it in months. When the Polynesians reached Hawaii, the civilizations of China, India, Persia, and Rome were active at the same time. When European explorers crossed the Atlantic, the Aztec and Inca empires were right there, functioning, populated, alive. No explorer in human history ever arrived at a destination to find that its inhabitants had existed and vanished millions of years earlier. The universe is not cruel, it is indifferent. It did not design these barriers to prevent contact. It did not arrange the distances, the speed limits, and the timescales with any intention at all. These features emerged from the fundamental physics of the cosmos, from the geometry of space-time, the properties of electromagnetism, the mechanics of gravity, and the thermodynamics of complex systems. The isolation of civilizations is not a punishment. It is a side effect, a structural consequence of the same physical laws that permit civilizations to exist. But the fact that it is unintentional does not make it less real, and the fact that it is structural means it cannot be overcome by ingenuity or determination. You cannot engineer your way past the speed of light. You cannot extend your civilization's lifespan to match the temporal gaps between active cultures in your region of space. You cannot make the galaxy smaller or make stars closer together. The barriers are not technical problems awaiting solutions. They are features of reality itself. Some will object that we cannot be certain of these conclusions, and they are right. We cannot. Our understanding of physics might be incomplete. There might be ways to circumvent the speed of light that we have not discovered. Wormholes, Alcubierre drives, or some as yet unimagined mechanism might permit faster than light travel or communication. Civilizations might find ways to extend their lifespans to millions or billions of years, bridging the temporal gaps that currently make overlaps so unlikely. We should not foreclose these possibilities with absolute certainty, but we should be honest about what they require. Every proposed mechanism for faster-than-light travel or communication relies on physics that is either entirely speculative or known to require conditions that may be physically unrealizable. Wormholes require exotic matter with negative energy density, a substance that has never been observed and may not exist. The Alcubierre warp drive, even after theoretical refinements that reduced the original energy estimates by many orders of magnitude, still requires exotic matter with negative energy density in quantities that no known process can produce. Quantum entanglement, despite popular misconceptions, cannot transmit information faster than light. The no communication theorem in quantum mechanics has been proven rigorously. Entanglement creates correlations between distant particles, but those correlations cannot be used to send a message. There is no known loophole. As for civilizational longevity, the challenges are equally daunting. A civilization lasting 1 million years would need to maintain technological coherence through geological scale changes in climate, stellar output, orbital dynamics, and biological evolution. It would need to survive every existential risk that 1 million years of existence presents, including risks we cannot currently anticipate. No known mechanism guarantees this kind of stability. The longest-lived complex organisms on Earth, certain species of trees and deep-sea creatures, achieve lifespans of thousands of years, not millions. The longest-lived human institutions span roughly a millennium. Extrapolating from these precedents to civilizational lifespans of millions of years requires an optimism that borders on faith. Hope is not prohibited, but hope should be calibrated against the evidence. And the evidence, as it stands today, points toward isolation as the expected condition of technological civilizations in the Milky Way. The SETI enterprise remains scientifically vital despite these odds. The search for technosignatures is one of the few endeavors that could, in principle, overturn this entire argument with a single confirmed detection. If Breakthrough Listen or any successor program detects an unambiguous artificial signal from a distant star, everything changes. The overlap problem does not prevent detection entirely. It makes it unlikely. Unlikely is not impossible, and the scientific and philosophical stakes are high enough that even a small probability of success justifies the effort. NASA's Technosignatures Science Analysis Group, chartered in 2024 and composed of leading researchers from SETI, astrobiology, and exoplanet science, represents a formal institutional commitment to this search. The group is evaluating which technosignature investigations should be integrated into NASA's broader research portfolio, identifying the most promising detection strategies and assessing the technology gaps that need to be closed. This is serious, rigorous science conducted by experts who understand the odds and pursue the search anyway. They are right to do so. The question is too important to abandon because the likely answer is uncomfortable. But the structural argument presented in this story does not depend on whether we eventually detect a signal. Even if we do, the three walls remain standing. A detected signal would confirm that another civilization existed at some point in galactic history. It would not enable dialogue. It would not create a relationship. It would not end the isolation. It would provide the knowledge that we are not unique, which is profound. But it would not provide the companionship that the dream of contact has always promised. And this is perhaps the deepest cut of all. The loneliness described in this story is not the loneliness of an empty universe. It is the loneliness of a universe that is full but unreachable. The pain is not that no one else exists. The pain is that they do exist, or did, or will, and it makes no difference. You cannot talk to them. You cannot learn from them. You cannot share your discoveries, your music, your mathematics, your fears, or your wonder with them. They are real, but they are ghosts, present in the history of the galaxy but absent from your experience of it, and you are a ghost to them. Every civilization that has ever arisen in the Milky Way likely went through the same process. They looked up, they wondered, they searched, they built instruments of increasing sensitivity and pointed them at the sky with increasing desperation. They found nothing. They debated what the silence meant. Some of them concluded they were alone. Some of them held out hope. All of them eventually went silent themselves, their last transmissions racing outward through a galaxy that had no one listening at the right place and time to receive them. And after they went silent, the galaxy did not mourn. It simply continued. Stars formed and died. Planets orbited in the darkness. Chemistry churned in oceans on worlds that had no one to name them. And somewhere, millions of years later, another civilization arose on another world, looked up at the same stars, and asked the same question. Are we alone? They searched. They found nothing. They went silent. The cycle repeated. It may have repeated 1,000 times, 1,000,000 times. Each iteration producing a species that briefly believed it might find a companion in the cosmos. Each iteration ending in the same silence. This is not a failure of any individual civilization. It is not a failure of intelligence or effort or technology. It is the operating condition of a universe where the distances are measured in light years, the speed limit is absolute, and the lifespans of civilizations are measured in millennia against a cosmic timeline measured in billions of years. The universe does not prevent civilizations from existing. It prevents them from coexisting in any way that matters. There is a version of this story that ends in despair. A universe where consciousness is cosmically irrelevant, where every thinking species is born into solitude and dies in solitude, where the grandeur of intelligence is mocked by the indifference of the physical laws that make it possible. That reading is available, and it is not dishonest. But there is another way to sit with this knowledge. The same physics that isolates us also produced us. The distances between stars that prevent contact are the distances that allowed stable solar systems to form. The speed of light that limits communication is the constant that makes coherent chemistry possible. The brevity of civilizational lifespans reflects the dynamism and complexity that make civilizations worth building in the first place. We are not separate from the universe that isolates us. We are expressions of it. The loneliness is real, but so is the fact that the universe generated minds capable of understanding their own loneliness. That is not nothing. And there is this. If the argument presented here is correct, then every moment of consciousness is rarer than we knew, not just biologically rare, temporally rare. Each civilization's window of awareness is a fleeting opening in an otherwise dark galaxy. The fact that you are alive during one of these openings, that you can look up and ask the question at all, places you in an extraordinarily select moment of cosmic history. Most of the galaxy's timeline is empty. Most of its volume is void. And yet, here, now, on this world, a species exists that can contemplate the whole structure and feel the weight of its own improbable existence. We are almost certainly not the first civilization to experience this. Others came before us, on worlds we will never find, in eras we will never observe. They looked at the same stars, they wondered the same things. They felt the same mixture of awe and terror that comes from understanding how large the universe is and how brief their presence in it would be. They searched for us, or for someone like us, and they did not find us. We did not exist yet, and others will come after us, long after the last human transmission has faded into the cosmic background, long after our sun has exhausted its fuel and swollen into a red giant. Other civilizations will arise around younger stars. They will develop their own telescopes, their own search programs, their own dreams of contact. They will look outward into a galaxy that appears silent and empty. They will debate whether they are alone. They will not know about us. Our signals will have passed through their region of space and continued onward into the void millions of years before their first radio receiver was built. We will be as invisible to them as they are to us. But perhaps that is not the end of the story. Perhaps some civilizations, faced with the understanding described in this story, choose to do something remarkable, not because they expect a reply, not because they believe contact is achievable, but because the act of speaking into the darkness has value in itself, regardless of whether anyone hears. A civilization that understands its own isolation might still choose to transmit, not a plea for contact, but a monument, a record of its existence encoded in the most durable medium available, electromagnetic radiation traveling at the speed of light through a galaxy that may never decode it. A civilization might encode its mathematics, its music, its history, its understanding of physics, its art, and its unanswered questions into a transmission designed to outlast the civilization that created it. Not a message in a bottle hoping to reach a specific recipient. A message in a bottle thrown into the ocean because the act of throwing it matters to the one who throws. This is not futile, or rather, it is futile in the narrow sense that it is unlikely to achieve contact. But it is not futile in the broader sense that it constitutes an act of testimony. A civilization that transmits a monument into space is saying, "We existed. We understood our situation. We knew the odds. And we chose to speak anyway, not because the universe demanded it, but because we demanded it of ourselves." The transmission is not for the listener. It is for the sender. It transforms the silence from something suffered into something answered, even if the answer reaches no one. Some civilizations may go further. They might encode their existence into physical artifacts. Probes launched toward promising stellar systems carrying records of a species that knew it would not survive to see the probe arrive. They might etch information into the surfaces of asteroids or the orbital parameters of artificial satellites designed to persist for millions of years. They might alter the spectral signature of their own star through megascale engineering, leaving a fingerprint that future civilizations could detect as unmistakably artificial even billions of years later. These are acts of cosmic defiance. They do not solve the isolation. They refuse to be silent within it. We have already begun this process ourselves. The Voyager spacecraft carry golden records inscribed with images, sounds, and greetings from Earth. The Arecibo message transmitted a brief encoded signal toward the globular cluster Messier 13 in 1974. These efforts are tiny, almost symbolic, but they represent something profound. A species that knows it is probably alone, reaching out anyway, not because the math favors contact, because something in the nature of consciousness refuses to accept silence without protest. That refusal is worth examining. It is not rational in the narrow sense. The probability that the Voyager records will ever be found by another intelligence is so small it rounds to zero. The Arecibo message will reach its target cluster in roughly 22,000 years, by which time humanity may be unrecognizable or extinct. These gestures do not improve our odds. They do not advance our technology. They do not bring contact 1 second closer. And yet we made them, and we felt, in making them, that we were doing something important. Why? Because consciousness is inherently testimonial. A mind that comprehends its own existence feels a compulsion to confirm that existence to something beyond itself. This is not a cultural artifact. It is not a product of Western individualism or human vanity. It is woven into the structure of awareness itself. To understand that you exist is to feel, at some deep and inarticulate level, that your existence should be witnessed, that the fact of a universe producing a mind capable of contemplating that universe is an event of sufficient significance that it should not pass entirely unmarked. The same capacity that allows us to understand our cosmic isolation is the capacity that makes that isolation feel intolerable. Understanding and protest arise from the same source. A mind that can grasp the silence is a mind that cannot accept it. This is why civilizations transmit even when they know no one is listening. It is why we carved symbols into stone before we had alphabets. It is why the oldest human art, handprints on cave walls tens of thousands of years old, consists of a being pressing its hand against rock and saying, "I was here." Consciousness does not merely observe the universe. It insists on registering its presence within it. And when the universe offers no audience, consciousness creates one, even if that audience is hypothetical, even if it is imaginary, even if it will never arrive. The act of testimony is its own completion. The message does not need a reader to have meaning. It needed a writer, and the writer existed. This is the terrifying truth the title of this story promises. Not that civilizations are rare, not that the universe is hostile, not that some great filter destroys every species before it can reach the stars. The terrifying truth is gentler than any of those explanations, and worse. The universe may produce mind after mind after mind, scattered across billions of years and hundreds of billions of stars, and each one may live and die in perfect isolation. Not because the cosmos is empty, but because it is too large, too slow, and too old for any two of its children to ever meet. The sky is full of stars tonight. Some of them may harbour worlds where other beings are looking up at this same moment, asking the same question, feeling the same silence. We will never hear them. They will never hear us. And the light travelling between us will arrive long after both of us are gone. The universe is not empty. It is full of civilizations that ended up alone.